So before I start, let me just say thank you to the organisers. This has been a great conference, and thank you for giving me this opportunity to speak today. So today I'm talking about cotraces and inner product enrichment of bicategories, and this is kind of part of a broader aim, I guess, to kind of take ideas from linear algebra and kind of copy them in category theory. And for me, this story kind of starts with the cotrace. So if you're teaching an undergraduate course in linear algebra and you want to explain what the trace is to some undergraduates, you maybe say that it's a kind of nice scalar invariant of a linear endomorphism. So it's some function, it takes in some linear map from a space to itself, and it kind of collapses it down into some scalar value, and this has nice properties. But when you teach undergraduates how to calculate the trace, you say, okay, well first fix a basis for your finite dimensional vector space, and then your linear endomorphism becomes a symmetric matrix, and then you just add along the diagonal. But this is kind of weird because it turns out that the trace is independent of the choice of basis, so you're kind of making a choice, but the choice doesn't really matter. So about 40 years ago, I came along this categorical perspective, which is kind of the trace exists because the category of finite dimensional vector spaces has duals. So the way this works, well, firstly we need some categorical notion of scalar, and a scalar is just given in a monoidal category by all the maps from the unit object to itself. This is always a monoid because you can compose, and it's always commutative because there's two ways to compose. You can use the tensor or the composition. And in 72, Callum gave this definition of a compact closed category, so a category with duals, and it's essentially a symmetric monoidal closed category where if you take HOMs into the unit object, what you get is a strong monoidal involution. So normally, HOMs into the unit object we write with a star, and we think of this as being the dual. And so the kind of motivating example is finite dimensional vector spaces. Dolden Pupper pointed out that the trace can just be defined in any compact closed category. So because you're closed, you have this evaluation map here, and because you've got duals, you can dualize, and what this means is you can kind of stick a morphism into the unit object at one end, stick a morphism out of the unit object at the other end, and then stick any kind of linear or any endomorphism in the middle. So this gives a scalar because it's a map from 1 to 1. And most of the kind of interesting examples in the one category case are kind of something to do with vector spaces. But about 15 years ago, I think, Simon Bullison gave a talk at CT about examples where we're thinking in terms of bicategories. So we're bumping up a dimension now, which means that scalars aren't just a commutative monoid, but they're a symmetric monoidal category. And the trace isn't just a function, but it's a functor. So the first example is sets and relations. This forms a bicategory. You kind of have everything is self-dual because relations kind of don't really have a direction. And in this case, scalars are just either the empty set or the point which we think of this as being kind of like true and false. And the trace here tells you if you've got a relation from A to A, it tells you whether it's A reflexive. So this thing is true if X never relates to itself. So a similar example is spans of sets. And in this case, your scalars is just the whole category of sets, and your trace gives you an equalizer. So a span from A to A is just a pair of functions into A. You take their equalizer and that's the trace. There's a slightly more kind of algebraic example where you take the bicategory whose objects are algebras. Between them you have bimodules, and in this case scalars are vector spaces, and the trace gives you the co-invariance of some bimodule. Then there's a kind of derived version of this story where you take derived categories of bimodules and then you get Hochschild homology. I think my favorite example is categories and profunctors. So in this case, the trace just gives you the co-end of a particular profunctor. And then there's also some kind of topological examples. So a kind of simple one is if you take a topological group and construct a bicategory out of points in the group and paths, then your scalars give you the fundamental group for the space, and the trace basically just takes a loop and then moves the base point so that it's at the unit for the group. But there are loads of other examples, so two vector spaces. Simon's got an example to do with varieties. There's a kind of topological thing to do with tangles, and then I think there's maybe some stuff to do with algebras or other with extra structure. But the thing that you might notice here is that each of these examples of trace has a kind of dual notion, right? So you look at covariance, you think, well, what about invariance? You look at Hochschild homology, you think, what about cohomology? You look at coends, you think, what about ends? So there's kind of some suggestion that there ought to be some dual notion to the trace, hence cotrace. So Simon and Bruce Bartlett and Ganser and Kapranov kind of had an approach to this, which is where you say, well, we're working in a two category or a bicategory. So we can consider the set of maps from the identity into any endomorphism. And generally speaking, when you think about this thing, you get the right kind of dual notion. So in the case of bimodules, what you get is the set of invariants. But the set of invariants should really have a vector space structure. It should be a scalar. And if you think about profunctors, you do get an end, but you get an end in set. But what you really want is an end in V, the thing you're enriching over. So this is kind of like a category error. This thing shouldn't be a set, it should have some other structure. And there's a kind of an alternative way of viewing this, which is by considering the fact that in each of these examples, we're not just closed symmetric monodally, but we're also closed compositionally. So what this means is we have all right Kahn lifts. I should point out that I use this notation, this lollipop notation for Kahn lifts, for various reasons that I won't get into now. But using this symmetric monodal closed structure, and also the Kahn lift structure, you could take the identity and then turn it into a map out of the unit object into an internal Hom object, do the same thing with your endomorphism, and then just take the right Kahn lift between the two unit objects. So this is kind of a potential as a definition of cotrace, and this actually first appeared in a paper of Dane Streets in 1997. It's kind of just buried in there. They don't really do much with it. But it's kind of interesting because this notion of trace, so the cotrace doesn't require the existence of duals. You just need symmetric monodal close and composition close. And in most of our examples, this gives the exact thing that you expect, which kind of suggests that this notion of two-trace and this notion of cotrace should really be somehow the same thing. And how they're the same thing? Well, through enrichment. So like I said at the beginning, I kind of want to take ideas from linear algebra and use them in category theory. And there's going to be this enrichment theorem, but it kind of comes from the idea of an inner product. So in particular, the Frobenius inner product. So if you have two finite dimensional Hilbert spaces, or inner product spaces, A and B, and you have two maps between them, two linear maps, living between those two linear maps is a scalar, and this scalar is given by an inner product. So the inner product is defined by taking the trace of F, followed by the adjoint of G. So we don't have adjoints, but we do have right Kahn lifts, and so we can kind of do an analogous construction, but in the case of bicategories, using this cotrace definition. And what this does is it essentially says, well, instead of having sets of two cells between our one cells, what instead we can get is a scalar. So we've got this scalar living between all of our one cells. And this happens in a really nice way. So kind of the statement for the theorem is that the bicategory B that you started with, you can actually just replace it with an enriched bicategory, where you're enriching over the category of scalar enriched categories. That's a bit of a mouthful, but essentially what it's saying is that the scalars between all your one cells behave like the sets of two cells, so you can compose, you've got this closed structure still, everything's symmetric monodal closed in fact. And in addition, each Hom category, so each category of one cells with scalars is powered and co-powered over the scalars. So there's this kind of weighted limit, co-limit condition as well. And one thing that I think is nice about this is that it means that we can think about, for example, adjoint profunctors in terms of scalars in the same way that you do with linear adjoints. So that's kind of nice. What does it give us in our examples? Well, kind of generally gives you the thing that you'd expect. So for sets of relations, obviously the one cells are just subset inclusion, and you just get that back. For spans, you were just enriching over a set, and you just get the thing you started with. For bimodules, well, maps of bimodules have a pointwise vector space structure, so you recover that. I think for me, again, the most interesting example is profunctors. So this says that you start with this bicategory where you have V natural transformations between V profunctors, but then you just replace the sets of natural transformations with natural transformation objects. And then finally you've got this kind of this topological example where basically instead of homotopes of paths, you just replace them with loops. And something else that's kind of nice about this is this essentially it's a tautology. If you take the scalar that lives between the identity and your endomorphism, what you recover is the cotrace, and so this kind of explains the relationship between Simon's two-trace and this cotrace definition. It's just that the two-trace is basically the unenriched cotrace. Okay, so a sketch of the proof. Again, I'm going to keep reiterating this point that I want to lift some ideas from linear algebra and use them in category theory. So if you've got some monoidal category, there's this function which I like to call the spread, because it's in some sense opposite to trace. And essentially, if you've got some scalar S, you can kind of bump it up to be a map from any object A to itself, and you just do this by just tensoring your scalar with the identity on A. So if you do this in finite dimensional vector spaces, it just gives you the multiplication. So it takes the scalar and gives you scalar multiplication. But if we think about this in the case of finite dimensional Hilbert spaces, this map is linear, and so it has an adjoint, and its adjoint is just the trace function. So if we're thinking about now a symmetric monoidal bicategory, then there's a spread functor rather than a function, and you can prove that the cotrace is right adjoint to it. So in the same way that trace is kind of linearly adjoint to spread, cotrace is right adjoint to spread. And there's also a kind of dual version of this story, which is something I like to call co-spread, which is then right adjoint to the trace. Yeah, that's the right one. And you can use this to basically show that when you take the action of scalars on your Hom categories, so you do this by taking first the spread and then composing, what you get is an action of scalars on each Hom category in such a way that the action is closed. So there's this result which Richard Garner calls the fundamental theorem of enriched category theory. The earliest reference I could find for this was 1997. I think it might have existed before that. But it's kind of a generalization of the fact that symmetric monoidal closed categories are enriched over themselves. So if you've got some monoidal category B and it acts on some category C, then if that action has adjoint in an appropriate sense, then C is V enriched, and it's also co-powered, and the co-power is given by the action. So essentially, the kind of the main enrichment theorem just follows from a version of this fundamental theorem. Okay, so I think this is kind of cute. It's kind of neat. I kind of like the interplay between linear algebra and category theory in this kind of aesthetic way. But is it useful at all? Well, at the start I said when you were talking about trace, you want to think of this as a function with some nice properties. So does the cotrace have similar properties? Can we use them in any way? Well, the first property of a trace is that it's dual invariant. So if you take the trace of F dual, you just get the same thing as the trace of F. This is also true of cotrace. So that's quite nice. The trace preserves tensor products in some kind of sense, appropriate sense, and Cotrace kind of does, but laxly. Maybe the most famous property of the trace is that it's cyclic, so if you take the trace of F composed of G, it's the same as the trace of G composed of F. Cotrace doesn't have this property, but it has something similar. But actually, because we're in this two-category setting, this bicategory setting, there's kind of more things we can say about the trace than you would otherwise be able to say. So, for example, if you think about the trace in linear algebra, it's linear, which means it preserves weighted sums. In this setting of bicategories, the trace preserves colimits that are weighted by scalars, essentially because it's an adjoint, and the cotrace preserves limits which are weighted by scalars. So in some sense, limits and colimits are both behaving like sums. The cotrace is also lax-monoidal, which is maybe kind of surprising. And also, if you take the trace and the cotrace together, they form what's called a linear, in the sense of representation theory, a linear functor. And what I mean by that is they're action preserving. And I'm not going to go into the details for this, but just from those last two facts alone, we can define the cup and the cap product for Hochschild homology and cohomology. So this fact here means that you send internal monoids and internal modules to internal monoids and internal modules, and that means that Hochschild homology and cohomology have a cup and cap product. So one question that I would like answered is, can we do this for other homology theories? Is there some setup where we build bicategories and then we have varied Hochschild homology? So there's a paper by Nima Rasek and Catherine Hess where they talk about these things called shadows and how they relate to topological Hochschild homology of bicategories. So kind of trying to do this same story but in another setting. Okay, so this story isn't finished. There's some questions which are still kind of unanswered. So one is that you might have noticed a lot of our examples were kind of profunctorial in some sense. So sets and relations can really be thought of as special kinds of profunctors. Bimodules can be thought of as special kinds of profunctors. I think there's a reason for this, and I'm pretty sure you can, well, I know you can construct a pseudofunctor, which I'm going to call Cauchy, which starts with your bicategory and then replaces all of the objects with scalar-enriched categories themselves. And this works by basically doing a kind of formal Cauchy completion thing. So you start with an object, and then you send the object to the category whose objects are left adjoints from the unit into the object. So if you do this with categories, you just get back the Cauchy completion of the category. So I want to know if this is kind of nice, if this is an embedding in some sense, and whether it preserves enough structure that you can define all traces and cotraces as ends and coends whenever you have limits and colimits. And finally, this is kind of a slightly broader question. So it's true that in finite-dimensional Hilbert spaces, the dual of evaluation is also the adjoint of evaluation. And if you have some setup where you've got a bicategory B, where the dual of evaluation is left adjoint to evaluation, then the trace and the cotrace end up being the same functor. And in that kind of setup, I mean, this kind of maybe explains why in linear algebra you don't have a notion of cotrace, because the cotrace is the trace. So I want to know if there's some kind of theory of cotrace bicategories, which will then cover symmetric monoidal dagger categories, as well as these closed bicategories. Okay, so I went through that a bit quicker than I expected, but I'll finish there.
Thank you, Callum. Questions? Tom?
Thanks, Callum. That's a very nice story. It's possible I've asked you or Simon this question before, but anyway. In linear algebra, one of the most important properties of trace is that it's the sum with multiplicity of eigenvalues. Do you think there's any prospect of generalizing that fact to a broader context, or do you think it's just special to linear algebra?
I haven't thought about this in a while. I think this was maybe what I was trying to do here. So kind of, if you can think of the trace as a co-end or an end, then you've got an appropriate profunctor. So you kind of, you'd be able to replace your endomorphisms with profunctors, which are kind of like matrices, and then you've got more that you could say about that. So you could maybe try and do some determinanty stuff. I think it's possible. I think, yeah, that maybe, so there's this kind of fact where co-limits and limits both kind of behave like sums. So I think maybe there's something difficult because you don't have products. But yeah,
Thanks.
question.
Thank you. Other questions? All right, there being none, thank you, Callum.